All right, let's get right into it. We live in a world that is completely run by code, right? But have you ever really stopped to think about what makes good code, well, fast? What is that secret ingredient that lets our tech handle just massive amounts of data without grinding to a total halt? Today, we're going to pull back that curtain on the analysis of algorithms. It's the hidden science, really, that powers our entire modern world.
You know this feeling. I mean, we all do. It's that spinning wheel of death, that loading bar that's just stuck, the app on your phone that just freezes, and you're sitting there staring at the screen thinking, come on, why is this so slow? It's got to be one of the most universal frustrations of our digital lives. But it turns out this is not a new problem, not by a long shot.
In fact, this whole question, this obsession with speed and efficiency, it's actually one of the oldest, most fundamental questions in the entire history of computing. Seriously, long before we had laptops or smartphones, the absolute pioneers of computation were already wrestling with this exact same challenge.
And get this question was asked way back in 1864. The person asking? Charles Babbage, the guy widely known as the father of the computer. He wasn't just wondering if a machine could do the math. No, he was already obsessed with finding the fastest way to do it in the shortest time.
And this is the machine he was talking about, the analytic engine. It's just this incredible marvel of gears and levers designed back in the age of steam. So for Babbage, his question was, quite literally, how many times do I have to turn the crank to get the answer? He knew, even then, that the method you choose to solve a problem, well, it mattered just as much as the machine itself.
So let's fast forward to today. The cranks are long gone, replaced by processors that are billions of times faster. But the struggle? It's exactly the same. Only now, we have a name for what happens when we ignore Babbage's question. We create what are called performance bugs, and trying to fix them involves a few key players.
You can almost think of it like a little play with a cast of characters. So first step, you've got the programmer. Their main goal, just get a working solution at the door. But then you had the client, the one paying for it all, and they need that solution to be fast and reliable. And then, sort of watching from the sidelines is the theoretician, who wants to understand the fundamental principles of why one solution is way better than another. The problem is, their goals don't always line up.
So why do we go through all this trouble of analyzing algorithms? I mean, why not just write code that works and call it a day? Well, it's about being professional. It lets us predict how a program is going to behave before it gets overwhelmed and crashes. It gives us a scientific way to compare different strategies, not just guess which one feels faster. It lets us provide guarantees to a client that their system isn't going to fall over on Black Friday. And of course, it helps us understand the deep theoretical basis of how computation works.
But let's be real for a second. While all of that academic stuff is important, the number one most critical, down-to-earth reason is to avoid those nasty performance bugs. You know the kind. The program works perfectly fine on your machine, with a tiny bit of test data, but then it completely collapses the second a client tries to use it with a real-world large-scale data set. It's the kind of bug that absolutely kills products. Okay, so how do we actually avoid these bugs? We can't just wing it. Well, back in the 1970s, the legendary computer scientist Donald Knuth had this powerful insight. We should treat programming like a science. We can use the good old scientific method to understand how our programs perform. And here's what that actually looks like. You start by just observing. You run your code, you time it, you measure how much memory it's using. Then you hypothesize. You try to come up with a mathematical model that explains what you're seeing. But here's where the magic happens. You use that model to predict what will happen if you suddenly throw, say, 10 times more data at it. Then you verify it by running more experiments to see if you are right. And you just keep repeating this cycle, validating, refining, until your model and reality are in perfect agreement. It's a rock-solid way to find the truth. Okay, so we have a method. But you might be sitting there thinking, does it really matter that much? I mean, how big of a difference can choosing one algorithm over another actually make? Well, this is the part where theory smashes into reality, and the results are, well, they're astonishing. So let's take a look at a really famous case study, something called the discrete Fourier transform, or DFT. Now, in simple terms, this is just a mathematical tool that lets you take a complex signal, like, say, a sound wave, and break it down into all the individual frequencies that make it up. It's super, super important for processing pretty much any kind of digital signal. Now, it turns out there are two ways to do this.
First, there's the obvious brute force way. Let's call this the turtle's path. If you have n pieces of data, it takes roughly n squared steps to finish. Basically, for every single piece of data, you have to compare it to every other piece of data. The workload just balloons like crazy. But then there's the rocket's path, a brilliantly clever solution called the fast Fourier transform, or FFT. And it only takes n log n steps, a much, much shorter trip to get to the exact same answer. And just look at what that difference means on a graph. The n log n line, our rocket path, it barely even moves up. It just kind of crawls along the bottom. But the n squared line, it goes ballistic. It just explodes upwards. That curve right there is the visual definition of a system grinding to a halt. It's the spinning wheel of death we were talking about right at the beginning. So here's the really important takeaway. This isn't just some abstract graph in a computer science textbook. That exploding curve represents a wall, a hard limit on what is technologically possible. And finding a clever way to get off that explosive curve and onto the flat one, well, that changes everything. It turns science fiction into something you can literally hold in your pocket. I mean, that huge gap between those two lines on the graph, that's the difference between a DVD player being an impossible fantasy and an everyday object you can buy for 20 bucks. It's the difference between a digital camera being a wild dream and something that's on every phone. Without that fast algorithm, these devices just wouldn't exist, period. In fact, that n log n breakthrough, the fast Fourier transform, is what made all of this possible. The way your photos get compressed into JPEGs, the way you watch DVD or stream a video, even the way an MRI machine works at a hospital, or how astronomers analyze signals from deep space, it all comes back to this one, single, elegant algorithmic discovery. And this isn't just a one-time thing. This principle pops up everywhere. Take simulating how billions of stars in a galaxy interact with each other. The brute force, n squared way, is just computationally impossible. You couldn't do it with all the computers in the world. But a clever n log n algorithm, in this case one called the Barnes-Hut algorithm, suddenly makes it possible, opening up whole new frontiers in science. So that leaves us with this final, really fascinating question to think about. We've seen how one single clever algorithm can completely revolutionize technology and science. It really makes you wonder, what impossible problems that we face today, in medicine or climate science or AI, are just sitting there, waiting for that one elegant, efficient algorithm to come along and suddenly make them possible?